Okay, I think this will probably be the you know the section that people are really not quite used to. Zeros of polynomial functions. We talk about um, a few things in this section. We learned how to find the rational zeros, possible rational zeros. What they do is just the factor, the leading coefficient and the constant for a polynomial with integer coefficients. And then you just divide those factors, and then that will give you a bunch of possible rational zeros. That means when you try to solve the polynomial equation, you might have a couple of rational solutions. Okay, that's what it means by rational zeros. All right, and other than that, then we discuss about the upper bounds for zeros of polynomial function. Okay, so this is not just for coefficients of integers. This polynomial p can be any polynomial. The coefficients of the polynomial can be any number. It doesn't have to be uh, uh, integers, but of course, it makes it a little easier for the integers. All right, so we just um, and do the syntactic division with the integers. All right. So I think we did one example last time about on how to find the upper bounds of real zeros from polynomial. What you do is just pick up positive number and then do the syntactic division, and then you look at the bottom row of the syntactic division. Okay, and depending on whether the leading coefficient an is positive or negative, then you have two different situations. In the case of the leading coefficient, the an is positive, uh, then you need to have all the numbers at the bottom row of syntactic division non-negative. So it's either 0 or positive. Then you can claim that the number you use for the syntactic division is the upper bound for the real zero p of x. So that's a little tricky. Is you know. So we talk about the upper bounds of real zeros of polynomial. And then similarly, we can also determine whether a number is a lower bound of real zeros of a polynomial p. All right. So what does it say here for the lower bounds? Okay. Again, you do syntactic division. Okay. But then, the conclusion is different. So what it says is you pick up a negative number. Okay, let's say b is a negative number, and you do syntactic division of the polynomial with the number b, and then what you see is in the bottom row of the syntactic division, alternating sign. Okay, so the numbers in the bottom row of the syntactic division alternating sign, then b is a low bound for real zeros of p. All right. So, but you have to use a negative number for b for the lower bound. And whenever you have 0 appearing on the bottom row, then it works for both positive and negative. You can treat it as both positive or negative. Okay, so 0 is a good number. So let's just do one example to find the largest negative integer lower bound for real zeros of polynomial p equal to 2x cubed plus 7x squared minus 4x minus 14. So we can only determine whether a negative is a lower bound or not, real zeros of polynomial or not. And we want to find the largest negative integer lower bound. So when you say the largest negative integer lower bound, it means the largest negative integer number is -1. Okay. So then that's the first number you check. If -1 doesn't work, then you check -2 until you find a negative number integer that is indeed a lower bound for the real zeros of polynomial by using the rule in here. And then that will be the large negative integer, lower bound. All right. Okay. So we're gonna start from -1 for B. As I said again, you can only find the lower bound with negative numbers. Okay. And then see what ends up with the syntactic division. So just do syntactic division. So for -1 outside, you get all the coefficients of the polynomial 2, 7, -4, -14. Move down 2 and then multiply -1 with 2, you get -2. 7 plus -2 is 5. 5 times -1, you get -5. -4 plus -5 is -9. -1 times -9 is 9. 9 plus -14 is -5. So you can see the numbers at the bottom row of syntactic division are not alternating in sign. Okay, it's not like positive, negative, or negative, positive. So the one, it's not a lower bound for the real zeros of the polynomial. So that means there are some solutions. If you solve the polynomial equation px equals 0, there are some solutions less than -1. Okay. So then you try -2, the next number. See if that's the lower bound. Okay. So do the syntactic division with -2. You move down 2 and multiply -2 by 2, you get -4. Same plus -4, you got 3. 3 times -2, you get -6. -4 plus -6, you get -10. And then -10 times -2, you get 20. 20 plus -14, you get 6. So again, it's not alternating. Okay, the first two numbers are both positive. Okay. So -2 is not a lower bound for the real zeros of polynomial. Then you try -3, do the same thing. Okay. Move down 2 and multiply 2 with -3, you get -6. 7 plus -6, you get 1. 1 times -3, you get -3. -4 times plus -3, you get -7. 7 times -3, you get 21. 21 plus -14, you get 7. So again, the bottom row is not alternating sign. You get 2 and 1 both positive. And then -3 is not a lower bound for real zeros, so the polynomial. So do the next number, -4. So it decreases, 1 by 1 until you find the right number. Okay. So move down 2, multiply -4 by 2, you get -8. 7 plus -8, you get -1. -4 times -1, you get 4. -4 plus 4 is 0. -4 times 0 is 0. And then -14 plus 0 is -14. So we do get a positive, negative, 0, and negative. And again, 0 can be regarded as either positive or negative. So that's indeed satisfies the criterion. The numbers at the bottom row of the syntactic division alternating sign. So that means -4 is indeed a loop for the real zeros of the polynomial. So that means when you try to solve the equation of 2x cubed plus 7x squared minus 4x minus 14 equal to 0, all the solutions, all the real solutions must be greater than or equal to -4. Okay, so even though we might not be able to, find the exact solutions of this equation, we can tell what range the solutions are, right? So -4 is the largest negative integer lower bound for real zeros of px. Okay. Any questions for this thing? All right, no question then. We have one more page for this section, and that's another, strange thing. You probably don't use that too much, but everything is for solving the polynomial equation, basically, and what we can do about it. If we cannot solve it, there are a lot of polynomial equations with high degrees. You may not be able to solve them analytically, but at least you can say something about it. You can tell, what possible rational solutions for a polynomial equation with the integer coefficients, right? And whether they are solutions to the polynomial equation, you can check it one by one by doing the syntactic division, actually. Okay. And then you can also find the lower bound and the upper bound of the solutions of this equation. Then the solutions of the polynomial equation have to be between some numbers, within some range. And this is the other thing we can say about the zeros of polynomial functions. Okay, that's called Descartes' rule of signs. All right. And what it does is it can tell you how many possibly, how many positive real zeros and how many negative real zeros the polynomial equation may have. Okay. So that's another thing which will be helpful for us to determine the future of the solutions of the polynomial equation. So let P be a polynomial with the terms arranged in order of these decreasing powers of x, and that's what we usually do. You usually write the highest power in the first. The number of positive real zeros of P is equal to the number of variations in the sign of P. So you look at each term in the polynomial and see how many variations that the polynomial has. So a variation means a change either from positive to negative or from negative to positive. Okay. Or to that number decreased by even integer. Okay. So how many? How many positive zeros of the polynomial equation? The polynomial is the number of variations in the polynomial, or that number of variations in the polynomial decreased by even integer. Okay, and we're going to see an example. So let's just look at one example. We need to find the possible numbers of positive and negative real zeros of the polynomial p equals x to the fourth minus 5x cubed plus 5x squared plus 5x minus 6. So in order to find the possible numbers of positive real zeros, so if you try to solve this equation, x to the fourth minus 5x cubed plus 5x squared plus 5x minus 6 equal to 0, how many positive solutions we might have? You just count the variations in the polynomial itself. Okay, from x to the fourth to negative 5x cubed, that's one variation. From negative 5x cubed to the 5x squared, that's another variation. From 5x squared to 5x, that's another variation. Okay, from 5x to negative 6, that's another variation, you see? So there are 3 variations in total. So that means based on the rule in here, the possible number of positive real zeros of the polynomial is either 3 or 2, 3 or 1. Okay, so the variation is 3, but It could be 1. It says, or to that number decreased by even integer. 3 minus 2 is equal to 1. So it could be 3 or 1. So, but at least we can say, there are at least 1 positive real solutions, right, for the polynomial equation, isn't it? Okay, so that's the possible positive real zeros. How about the negative real zeros? How do you determine negative real zeros of P? You still use the variations, but this time you use the variation for P of negative x. Okay, so the number of negative real zeros of P is equal to the number of variations in sign of P of negative x, or to that number decreased by the integer number. Okay, so you plug in negative x for x and see how many variations it has. Okay, so why don't we just do the same example with negative x. So negative x for x in the polynomial, we get negative x to the fourth minus 5 times negative x cubed plus 5 times negative x squared plus 5 times negative x minus 6. So the first term will be positive because it's fourth power, and then negative x is negative, so you get another negative in the front, and it becomes positive 5x cubed, right? And again, 5 times the negative x squared, you get the x squared because it's square negative number. You got positive, and then we got negative 5x and minus 6. So how many variations in here? From x to the fourth to 5x cubed is not a variation. From 5x cubed to 5x squared is not a variation. From 5x squared to 5x, it is a variation. From negative 5x to negative 6, that's not a variation. So there's only one variation. So according to the rule, there is indeed one negative real zero P. Okay, so now you can tell that when you try to solve this polynomial equation, you're going to have, for sure, there is one negative solution. And you may have 1 or 3 positive solutions. Okay, so that tells something, right? So that's the end of this section. It's a little, hard somehow for this section, but we're trying to solve the polynomial equation, and it's a hard job. Keep in mind, and that's all we can do about it. Any questions for this section? I have no question. Then why don't we just move to the next section? And 3.4, I think. So I don't know if we can finish it or not. We might. That's a short section, actually. Well, it is short, but it's important. It's the fundamental theorem of algebra. Okay, whenever you see something fundamental or fundamental theorem, that means it's extremely important because that's what everything is based on. So what does it mean by the fundamental theorem of algebra? What does it say? It says if P is a polynomial function of degree greater than or equal to 1, the complex coefficients, because we are talking about a general polynomial function, okay? Then P has at least one complex zero. So if you try to solve any polynomial equation, okay, any polynomial equation, you're going to get at least one complex solution, okay? Sometimes it could be real, but in general, it be complex. And this polynomial can be anyone with even complex coefficients. The coefficients of the polynomial don't have to be all real. Okay, and then if you use the factor theorem, or factoring theorem we discussed in 3.2, I think. Then you can factor in the polynomial by using this complex zero. So let's say the polynomial P has a complex zero, C1, and then you can factor x minus C1 from the polynomial, and you can get a reduce the polynomial of x, another polynomial. It's very easy to understand if you forget. When you try to solve the equation for Px equals 0, you factor it. For each factor, you set equal to 0, then you solve. For each one, you get the solutions. So obviously, if you do it in here, you're going to get a C1 as a solution or a 0, right? And the theorem just says the converse. Okay. We'll just use the converse of that. So you can rewrite Px factored form like this, by using the fundamental theorem of algebra. Well, if you use the fundamental theorem of algebra again on Q, then because Q is a polynomial or polynomial function, then you can say it has at least one complex zero. So then you can factor Q as maybe x minus C2 if C2 is a 0 of Q, and times some other polynomial function R. Okay, and then you use fundamental theorem of algebra on the polynomial R, and then you get another 0 C3 maybe for R, and then you can factor R again and again. So you just proceed with this procedure until you factor everything to the end. Factor the whole polynomial P into linear factors. Okay, so whenever you have a polynomial with degree greater than 1, you can always find it as 0, so you can factor it out a linear factor. So at the end, when you complete the whole process, you actually factor the whole polynomial P into all linear factors, because if this one is not the linear factor, then you can use the fundamental theorem to factor it. Okay. So and then we got the so-called linear factor theorem, which is a direct consequence of fundamental theorem of algebra. So obviously, as I said, if P equals a n x to n plus a minus 1x minus 1 plus all the terms down to x1, x, and plus a0, and then E has exactly n linear factors. You can always factor n down to linear factors. And obviously, if you write x minus c1, x minus c2 to x minus c, and then you still have an in the front to multiply the whole thing, so that the leading coefficient is an. Okay. So this c1, c2, c3 to cn are complex numbers. Okay, in general. What's the question? I just saw somebody raise the hand. Did anybody raise a hand? No? Any questions? Okay, no question. So what does it say in this linear factor theorem? That means you can always solve any polynomial function, theoretically, okay? We may not know how to solve it, but for any polynomial equation, we can always solve it. And the solutions, of course, can be either real or complex. Okay, maybe all of them are complex. Sometimes all of them are real. In other cases, there could be some of the solutions real and the others complex. All right. Okay, then you know, since we can factor polynomial p into linear factors, then when we solve it, we just set each factor equal to 0, then guess what? We're going to get n solutions. So then we come up with the number of zeros of polynomial function then, okay? If p is a polynomial function of degree n greater than or equal to 1, then p has exactly n complex zeros. That means the polynomial equation has exactly n solutions. C1, C2, C3, up to Cn. Those are the zeros. Okay, you know, complex zeros in general. Some of them may be equal. C1 may be the same as C2. So then you should count zeros according to its multiplicity. So for example, if you got the C1 equal to C2, then when you try to solve this polynomial equation, you don't get the distinct zeros. You get n minus 1 distinct zero, but if you count C1 and C2 as two zeros, then the total number of zeros of polynomial is still n, right? Okay, so that takes into account the multiplicity of the zeros. Any questions? Yes, at least it looks pretty beautiful, right? All right. So I guess let's do some examples. Okay, using all the knowledge we just learned in this week, try to solve some polynomial equations. Okay. So in this example, we need to find all zeros of the polynomial p, which is x to the fourth minus 4x cubed plus 8x squared minus 16x plus 16. You note that the polynomial has all integer coefficients. Okay, all the coefficients of the integer of the polynomial are integers. So we can, try to find the rational zeros. We can use that theorem. Remember, if all the coefficients of a polynomial are integers, then we can try to, find the rational zeros of the polynomial. What we need to do is just factor the leading coefficient and the constant. Okay, the leading coefficient an is 1, so x to the fourth has a coefficient of 1, and the last numbers the constant is 16. So we just factor those two numbers, and obviously for n equal to 1, you don't have anything to factor out, so it's just the plus or minus 1. Okay, remember, include both positive and negative, positive and negative. But for 16, we can factor it as a bunch of numbers, and so the factors of 16 will include plus minus 1 plus minus 2 plus minus 4 plus minus 8 plus minus 16. You should write all the possible factors from those two numbers. So then you divide the factor of a0, 16, by the factors of an, 1. And when you do that, you get a possible rational zeros of polynomial p, which are plus minus 1, plus minus 2, plus minus 4, plus minus 8, plus minus 16. In this case, it's rather simple because you just divide by plus minus 1. Okay, so you get all those numbers, factors of a0, 16. And then you just do the static division of p using those numbers. You just try it one by one. And then you find actually, if you do that, okay, so I'm not going to go through all this synthetic division with those numbers. but I just show that it really is a real zero of the polynomial. And it turns out that 2 is indeed a real zero of the polynomial. So just do the synthetic division with 2 and what do we get? So put all the coefficients here, 1, -4, 8, -16, 16. Once again, just reminder if some terms are missing, in between in P, then you should add 0, right? So do the synthetic division with 2. So move down 1 and multiply 2 and 1 you get 2, and -4 plus you get -2. 2 times -4, 2 you get -4. 8 times -4 you get 4. 8 plus -4 is 4. 2 times 4 you get 8. -16 plus 8 you get -8. 2 times -8 you get -16. 16 times plus -16 you get 0. So 2 is indeed the real of the polynomial or rational 0. Actually, it's an integer 0, in fact, because the last number is 0. That's the remainder. You don't have any remainder, so that means it is indeed a 0. Then you can factor the polynomial as x minus 2 times x cubed minus 2x squared plus 4x minus 8. Okay, because there's no remainder again. All right. Again, you should read the reduced polynomial, the last row of the bottom row of the synthetic division. Okay. So from x to the fourth, if you divide by x minus 2, you should get the x cubed as the first term. That's the way to write down the reduced polynomial from the result of synthetic division. And then what you do next? You do the synthetic division with the reduced polynomial. So you have to repeat this process again. You need to factor the leading coefficient, which is 1 here, so we don't have to do anything about that. But the last number is 8, or -8, it doesn't matter. You factor 8, you get the plus minus 1 plus minus 2 plus minus 4 plus minus 8. And then divide by the factors of the leading coefficient 1. So you get the plus minus 1 plus minus 2 plus minus 4 and plus minus 8 as possible rational zeros of this reduced polynomial. And then you just check those possible rational zeros of the reduced polynomial by synthetic division again. So just repeat the same procedure, and then you might be lucky to find another rational zero. Okay. So it's that actually works, and indeed you find 2 as a rational zero for the reduced polynomial. So it shows in here that you do the synthetic division with the reduced polynomial. You got the 1, -2, 4, -8, and do synthetic division with 2. Okay, so move down 1, and 2 times 1 you get 2, -2 plus 2 is 0. 0 times 2 you get 0, 4 plus 0 you get 4. 2 times 4 you get 8, and -8 plus 8 you get 0. So again, the last number at the bottom row of synthetic is 0. So we indeed get another 0 of the polynomial. So then you can rewrite the reduced polynomial as x minus 2 times x squared plus 4. Remember when you divide the the reduced polynomial x cubed minus 2x squared plus 4x minus 8 by x minus 2 you get the x squared as the leading term. Okay, so the coefficient at the bottom row, the coefficients for the next reduced polynomial. Okay, so you just get x squared as the leading term and 4, and there's no linear term because the coefficient for linear term is 0. So then the whole polynomial P is actually x minus 2 times reduce the polynomial, which can be reduced further as x minus 2 times x squared plus 4. And then you just set each factor equal to 0, you get the x equal to 2 or x squared plus 4 equal to 0. So you get the x minus 2 equal to 0 twice, but they just give one answer, right? And then we know how to solve for x squared as 4 equal to 0. You move 4 to the right to get negative 4, so x squared equal to negative 4. You take the square root, you get the 2 complex zeros or solutions, which are plus or minus 2i. Okay, just keep in mind. So there are 3 distinct zeros of the polynomial p, and the real 0 2 is actually double real 0. It has multiplicity 2, and then you get 2 complex zeros plus or minus 2i. Okay, or imaginary zeros. Any questions? Looks like we have 2 more pages. We cannot finish this section today. We're going to do it on next Wednesday. Okay. So let me just stop the recording.